Section 1 Introduction. Let's start with an introduction. A significant portion of our scientific knowledge is tucked away in books or published in scientific journals, typically in the form of portable document format, PDF, files. After HTML, PDFs are the second most common data format on the internet, accounting for 2.4% of the common crawl. However, extracting information from these files into other formats is a challenging task. This is particularly true for specialized documents like scientific research papers, where the meaning of mathematical expressions often gets lost in translation. Existing optical character recognition (OCR) systems, such as Tesseract OCR, are great at identifying and categorizing individual characters and words in an image. However, they struggle to understand the relationship between these elements due to their line-by-line approach. This means they treat superscripts and subscripts the same way as the surrounding text, which is a significant problem when dealing with mathematical expressions. In mathematical notations like fractions, exponents, and matrices, the relative positions of characters are vital. Transforming academic research papers into machine-readable text also enhances the accessibility and searchability of science as a whole. Currently, the information in millions of academic papers is not fully accessible because they are trapped in an unreadable format. Existing databases, such as the S2ORC dataset, capture the text of around 12 million papers using GROBID, but they lack meaningful representations of mathematical equations. To address this issue, we introduce Nougat, a transformer-based model that can convert images of document pages into formatted markup text. The main contributions of this paper include the release of a pre-trained model capable of converting a PDF into a lightweight markup language. Now, let's move on to related work. Optical character recognition, OCR, is a widely studied field in computer vision with a range of applications, such as document digitalization, handwriting recognition, and scene text recognition. More specifically, recognizing mathematical expressions is a heavily researched subtopic. Grammar-based methods for handwritten mathematical expressions have been improved upon by different encoder-decoder models. The fully convolutional model was succeeded by various RNN decoder models, both for handwritten and printed formulas. Recently, the decoder as well as the encoder were replaced with the transformer architecture. Visual document understanding, VDU, is another related area of deep learning research that focuses on extracting relevant information from a variety of document types. Previous works rely on pre-trained models that learn to extract information by jointly modeling text and layout information using the transformer architecture. The Layout LM model family uses a masked layout prediction task to capture the spatial relationships between different document elements. Open-source solutions with similar goals to ours include GROBID, which parses digital-born scientific documents to XML with a focus on the bibliographic data, and PDF2HTMLEX, which converts digital-born PDFs to HTML while preserving the layout and appearance of the document. However, both solutions fail to recover the semantic information of mathematical expressions. Section summary. The majority of scientific knowledge is stored in PDF format, which is difficult to extract and convert into other formats, especially for specialized documents like research papers where mathematical expressions are lost. Existing OCR engines fail to understand the relationship between characters, making it challenging to accurately represent mathematical equations. Our proposed model, Nougat, is a transformer-based approach that can convert images of document pages into formatted markup text, addressing the need for machine-readable academic papers and enabling accessibility and searchability of scientific information. Section 3 Model. We're going to delve into the model we've developed for visual document understanding, VDU. In the past, VDU methods have either depended on optical character recognition, OCR, text from an external tool or focused on specific types of documents like receipts, invoices, or forms. However, recent research has shown that it's not always necessary to use an external OCR engine to get competitive results in VDU. Our model is built on an encoder-decoder transformer architecture, which allows for an end-to-end training process. We've based our model on the donut architecture, and it doesn't require any OCR-related inputs or modules. The network implicitly recognizes the text. Let's break down the two main components of our model, the encoder and the decoder. The encoder takes a document image, trims the margins, and resizes the image to fit a fixed rectangle. If the image is smaller than the rectangle, we add padding to ensure each image has the same dimensions. We use a SWIN transformer, a hierarchical vision transformer that divides the image into non-overlapping windows of a fixed size and applies a series of self-attention layers to gather information across these windows. The model then outputs a sequence of embedded patches, where D is the latent dimension and N is the number of patches. The decoder takes the encoded image and decodes it into a sequence of tokens using a transformer decoder architecture with cross-attention. The tokens are generated in an auto-regressive manner, using self-attention and cross-attention to attend to different parts of the input sequence and encoder output respectively. The output is then projected to the size of the vocabulary, V, producing the logits. We use the M-BART decoder implementation and the same tokenizer as Taylor et al., as their model is also specialized in the scientific text domain. Now, let's talk about the setup. We render the document images at a resolution of 96 dpi. Due to the restrictive possible input dimensions of the SWIN transformer, we choose an input size that is between the US letter and DIN A4 format. The document images are resized and then padded to achieve the desired input size. This input size allows us to use the SWIN base model architecture. We initialize the model with pre-trained weights. The transformer decoder has a maximum sequence length of 4096, which is relatively large because academic research papers can be dense and tables, in particular, require a lot of tokens. The BART decoder is a decoder-only transformer with 10 layers. The entire architecture has a total of 350 million parameters. We also experiment with a smaller model, 250 million parameters, with a slightly smaller sequence length of 3584 and only 4 decoder layers. During inference, the text is generated using greedy decoding. For training, we use an Atom W optimizer to train for 3 epochs with an effective batch size of 192. Due to training instabilities, we choose a learning rate that is reduced by a factor of 0.9996 every 15 updates until it reaches a certain minimum value. Section summary. The model proposed in this paper is an encoder-decoder transformer architecture for visual document understanding, VDU, that does not rely on external OCR engines. The visual encoder uses a SWIN transformer to process document images and generate embedded patches, while the decoder utilizes a transformer decoder architecture with cross-attention to decode the encoded image into tokens. The model is trained for 3 epochs using an Atom W optimizer and achieves competitive results in VDU without the need for OCR-related inputs or modules. Section 3.2 Data Augmentation. In our work, we found that data augmentation can be a powerful tool for improving the performance of image recognition tasks. This is particularly true when working with digital-born academic research papers, like we are. To mimic the inconsistencies and variations found in scanned documents, we apply a series of transformations to our data. These include techniques like erosion, dilation, adding Gaussian noise or blur, converting to bitmap, compressing the image, distorting the grid, and applying an elastic transform. Each transformation has a set chance of being applied to any given image. We use the Augmentations library to implement these transformations. To give you a better idea of how each transformation affects the image, we've included a figure in the paper. During the training phase, we also introduce random changes to the ground truth text by replacing tokens. This strategy has proven effective in preventing the model from getting stuck in a repetitive loop. You can find more details about this in the designated section of the paper. When it comes to datasets, we had to create our own since there isn't a paired dataset of PDF pages and corresponding source code available. We used open access articles from arXiv and a subset of the PubMed Central, PMC, open access non-commercial dataset to ensure a diverse range of layouts. We also included a portion of the Industry Documents Library, IDL, during the pre-training phase. For the arXiv dataset, we gathered the source code and compiled PDFs from over 1.7 million articles. To maintain consistent formatting, we processed the source files using LateXML, converting them into HTML5 files. This step was crucial in standardizing the LaTeX source code and removing any ambiguities, particularly in mathematical expressions. We replaced user-defined macros, standardized whitespace, added optional brackets, normalized tables, and replaced references and citations with their correct numbers. We then converted the HTML files into a lightweight markup language that supports various elements like headings, bold and italic text, algorithms, LaTeX inline and display math, and LaTeX tables. This ensured that the source code was properly formatted and ready for further processing. We also processed articles from PMC, which provides XML files with semantic information in addition to the PDF file. We converted these files into the same markup language format as the arXiv articles. However, we used fewer articles from PMC because the XML files often lack rich semantic information. For instance, equations and tables are often stored as images, which are not easy to detect. As a result, we decided to limit the use of PMC articles to the pre-training phase. Lastly, we used the IDL, a collection of documents produced by industries that impact public health. The University of California, San Francisco Library maintains this collection. Byton et al. Provided high-quality OCR text for PDFs from the IDL dataset. This text doesn't include formatting and is used only for pre-training to teach the model basic OCR of scanned documents. Section Summary. Data augmentation is used in image recognition tasks to improve generalization, and in this study, various transformations such as erosion, dilation, Gaussian noise, and image compression are applied to simulate imperfections and variability of scanned documents. Perturbations are also added to the ground truth text during training to reduce repetition. The authors created their own dataset by collecting source code and compiled PDFs from archive, processing them using late XML and converting them into a standardized markup language format. They also processed articles from PMC, but used fewer articles due to limited semantic information in XML files. Additionally, a portion of the IDL dataset was used for pre-training to teach the model OCR of scanned documents. Section 4.1 Splitting the pages. In this section, we'll discuss how we divided the pages of our documents. We started by splitting the markdown files according to the page breaks in the PDF file. We then converted each page into an image to create our final paired dataset. The LaTeX compiler automatically determines the page breaks of the PDF file during the compilation process. However, since we didn't recompile the LaTeX sources for each paper, we had to split the source file into parts that correspond to different pages. We did this by matching the text embedded on the PDF page to the source text. However, we encountered a problem. The positions of figures and tables in the PDF didn't always match their positions in the source code. To solve this, we removed these elements in a pre-processing step using a tool called PDF Figures 2. We then compared the recognized captions to the captions in the XML file and matched them based on their Levenshtein distance, which is a measure of the difference between two sequences. After splitting the source document into individual pages, we reinserted the removed figures and tables at the end of each page. To improve the matching process, we replaced Unicode characters in the PDF text with corresponding LaTeX commands using the PyLaTeX Inc. library. Next, we extracted the text lines from the PDF using a tool called mu-PDF and preprocessed them to remove page numbers and potential headers or footers. We then used a bag of words model with a TF-IDF vectorizer and a linear support vector machine classifier. We trained the model on the PDF lines, using the page number as the label. We then divided the LaTeX source into paragraphs and predicted the page number for each of them. Ideally, the predictions would form a staircase function, but in reality, the signal was noisy. To find the best boundary points, we used a similar logic to decision trees and minimized a measure based on the Gini impurity. This measure describes which paragraphs were considered for the split. After this initial document splitting, we tried to find the exact position within the paragraph. We did this by comparing the source text near the predicted splitting position to the last sentences of the previous page and the first sentences of the next page. We used the fuzzy search library for this. If the two dividing points were at the same location in the source text, we considered the page break accurate and gave it a score of 1. If the splitting positions differed, we selected the one with the smallest normalized Levenshtein distance and gave it a score of 1 minus the distance. To be included in the dataset, a PDF page had to have an average score of at least 0.9 for both page breaks. This resulted in an acceptance rate of about 47% of all pages. Section Summary. The process of splitting the pages involves rasterizing each page of the PDF file as an image and matching the embedded text on the PDF page to the source text. Figures and tables are removed in a pre-processing step and reinserted at the end of each page. A bag of words model with TF-IDF vectorizer and a linear support vector machine classifier is used to predict the page number for each paragraph, and a measure based on Gini impurity is used to find the best boundary points for splitting the document. Fuzzy matching is then performed to find the exact position within the paragraph by comparing the source text to the neighboring sentences of the previous and next pages. Pages with an average score of at least 0.9 for both page breaks are included in the dataset. Section 4.2 Ground Truth Artifacts. In this section, we're going to discuss some of the challenges we faced while working with our dataset and how they might have affected the quality of our data. We'll also talk about the performance of our model and how we evaluated it. Our dataset was pre-processed using a tool called LateXML, which can sometimes introduce artifacts or commands from unsupported packages into the source code. This can result in some inconsistencies in the HTML file, such as numbered subsection titles that aren't numbered in the original PDF. There might also be instances where figures or tables are missing due to processing errors. Another issue we encountered was with the splitting algorithm of the source code. In some cases, it might include text from the previous page or cut off words from the end. This is particularly true for invisible characters used for formatting, like italic or bold text, or section headers. For papers from the PubMed Central (PMC) database, inline mathematical expressions are written as Unicode or italic text. Display math equations or tables are often included as images, which our model ignores. All these issues can reduce the overall quality of our data. However, the large number of training samples we have helps to compensate for these small errors. Now, let's talk about the performance of our model. Our model focuses on the important content features of the page, ignoring things like the box around equations. We evaluated our model using several metrics, including 1. Edit distance. This measures the number of character manipulations, insertions, deletions, substitutions, needed to transform one string into another. We used a normalized version of this metric, where we divide by the total number of characters. 2. Blue. This metric was originally designed to measure the quality of machine-translated text. It computes a score based on the number of matching n-grams between the candidate and reference sentence. 3. Meteor. This is another metric for machine translation, but it focuses more on recall rather than precision. 4. F-measure. We also calculated the F1 score and reported the precision and recall. In a scientific research article, there are 3 main types of text: plain text, mathematical expressions, and tables. It's important to evaluate each of these components separately. This is because in LaTeX, the same mathematical expression can be written in multiple ways. Even though some variability has been eliminated during the late XML pre-processing step, there's still a significant amount of ambiguity present. This can lead to discrepancies between the predicted and actual results, even if the rendered formulas look the same. Moreover, it can sometimes be difficult to determine where a mathematical expression ends and the text begins, especially when dealing with numbers and punctuation. This ambiguity can lower both the math and plain text scores. As a result, the expected score for mathematical expressions is typically lower than for plain text. Section summary. The dataset used in this study may contain artifacts and unsupported commands due to pre-processing, resulting in missing figures or tables in the ground truth. The splitting algorithm of the source code may also include text from previous pages or cut off words. Despite these issues, the large number of training samples compensates for these errors. In the evaluation, metrics such as edit distance, blue, meteor, and F-measure are used to measure the performance of the model. It is important to separately examine plain text, mathematical expressions, and tables due to the ambiguity present in LaTeX notation. Section 5.3 Comparison. In this section, we'll discuss our findings and compare them with other methods. We've summarized our results in a table. As we anticipated, mathematical expressions were the most challenging to match with the original text. The discrepancies in plain text were mainly due to formatting issues and missing text caused by inline math. We used Grobid, a software that converts the output into an XML file. We then transformed this XML file into a markup language that's compatible with PMC or archive files. Grobid does offer some support for formulas, but it stores them as Unicode representations found in the PDF. To improve similarity, we replaced each Unicode symbol with its corresponding LaTeX command. However, Grobid sometimes mislabels small inline expressions as text. For the formulas it does identify, Grobid stores the coordinates of the bounding box. We tweaked the program to send these snippets to LaTeX OCR, an external formula recognition software. This allowed us to also get a signal for math modality. Unfortunately, the results were not very promising, mainly because Grobid missed a lot of formulas. The accuracy of equation prediction was also affected by the quality of the bounding boxes. The performance of the embedded PDF text alone was better than Grobid, which can be attributed to formatting differences for the title page or reference section. However, both Nougat small and base models outperformed the other methods and achieved high scores in all metrics. Interestingly, the smaller model performed just as well as the larger base model. We also noticed that the model often got stuck in a loop, repeating the same sentence over and over again. This happened in 1.5% of pages in the test set, and the frequency increased for out-of-domain documents. This is a known issue with transformer-based models when sampled with greedy decoding. Sometimes, the model alternates between two sentences but changes a few words, making strict repetition detection insufficient. It's even more challenging to detect when the model counts its own repetitions, which sometimes happens in the references section. Generally, this repetitive behavior occurs after the model makes a mistake, and it's unable to recover from this state. To address this, we introduced a random perturbation during training. This helped the model learn how to handle a wrongly predicted token. For each training example, there was a fixed chance that a random token would be replaced by another random token. This process continued until the newly sampled number exceeded a specified threshold, in this case, 10%. This approach didn't decrease performance, but it significantly reduced repetitions, especially for out-of-domain documents, where we saw a 32% decrease in failed page conversions. To detect repetition during inference time, we examined the largest logit value of the ITH token. We found that the logits after a collapse could be separated using a specific heuristic. First, we calculated the variance of the logits for a sliding window of size 15. Using this new signal, we computed variances again, but this time from the point X to the end of the sequence. If this signal dropped below a certain threshold, we chose 6.75, and stayed below for the rest of the sequence. We classified the sequence as having repetitions. During inference time, it's not possible to compute to the end of the sequence if our goal is to stop generation at an earlier point in time. So, we worked with a subset of the last 200 tokens and halved the threshold. After the generation was finished, we repeated the procedure for the full sequence. Section summary. The comparison of different methods shows that mathematical expressions have the worst agreement with the ground truth, while plain text discrepancies are mainly due to formatting ambiguities and missing text. Growbit, a program that converts XML files into compatible markup language, mislabels small inline expressions as text and has poor performance in identifying formulas. The model used in the study often gets stuck in a repetitive loop, but this issue is addressed by introducing random perturbations during training, resulting in a significant reduction in repetitions. To detect repetition during inference, a heuristic based on variance of logits is used. Section 5.5 Limitations and Future Work. Section 5.5 Limitations and Future Directions. Our model's usefulness is constrained by several factors. The first limitation is the issue of repetition, which we discussed earlier. Since our model is trained on academic papers, it performs exceptionally well with documents of a similar format. However, it's also capable of accurately transforming different types of documents. The majority of our dataset is in English. Preliminary tests on a small sample indicate that the model performs adequately with other languages that use the Latin script, although any unique characters from these languages are substituted with the nearest Latin alphabet equivalent. However, languages that use non-Latin scripts tend to cause immediate repetitions. In terms of generation speed, on a computer equipped with an NVIDIA A10G graphics card with 24 GB VRAM, we can process 6 pages simultaneously. The speed of generation is largely dependent on the volume of text on a given page. With an average of around 1400 tokens, the base model takes about 19.5 seconds per batch to generate content without any optimization for inference. This is considerably slower than traditional methods like GROBID, which can process 10.6 PDFs per second. However, our model isn't restricted to digitally born PDFs and can accurately interpret mathematical expressions. Looking ahead, our model is trained one page at a time, without considering the context of other pages in the document. This can lead to inconsistencies throughout the document, especially in the bibliography where the model was trained on various styles, or in section titles where numbers are sometimes omitted or imagined. While processing each page individually enhances parallelization and scalability, it may reduce the overall quality of the combined document text. The main challenge we need to address in future work is the model's propensity to fall into a repetitive cycle.